Hello everyone. Today we are going to talk about large-scale learning to rank. This will be our final project, and I'm Bofan Sun. First of all, I'm going to talk about the motivations. We think learning to rank is a new trend arising in the document retrieval, and Meta is very popular open source software to do the information retrieval task. However, Meta does not support learning to rank for now, so that we wanted to implement for Meta. Also, we know that there are three main methods to implement learning to rank, which are pointwise, pairwise, and listwise. In our case, we choose to implement pairwise. So for the problem definition, we think learning to rank is a supervised learning task with training data and testing data. To be our input, we need queries, document with relevance, and also the raw data. Then we can give the output, the rank list we predict. In summary, we want to combine the ranking features to optimize IR evaluation matrix. We wanted to use four features which supported by Meta, which are BM25, absolute discount, Dashler, and JM. For specific pipelines, we have five steps. For the first step, we need the datasets. We call it D. Then we will get a pair of document vectors from those datasets with scores and relevance. Then we will apply SGD algorithms on those pairs and repeat those process for each pair. Finally, we will have the weight vector to leverage the ranking scores. Then we will show you how to use our software. So first of all, we will teach you how to use Meta to get the dataset and the pairs document vectors. So the first step will be open the Meta in terminal. Then we will go to build and make. Then we need the raw dataset. We used the 20 news group to be our dataset examples. You can look at the dataset. We have the 20 news group in the data folder. We also need to create the corresponding queries files. As shown here, this is our queries test. We have 10 queries, just for simple. Then we need to go to the build and modify the config file, which is very important for Meta to run. So the important part start from line 9. We need to give the dataset names, also the corresponding corpus style and indexing. For indexing and corpus style, you can check more. You have more details in the Meta website. The second part would be query runner. We need to specify the queries as we created before. So the last part we want to modify for the config file would be the ranker part. First of all, we will use the method called BM25 with 3 parameters. If we don't provide those parameters, we will use the default one. After change this one, we can just run the query runner. As shown here, those are the results. The last one will be the query for friend, which is the 10th one. For each line, we have the document labels, the score for this document, and its document ID. We can also choose to use another method. For this one, this is the absolute discount. As we can show here, the results are similar. Also, we will show you how to do the Dashler. There are only one optional parameters. The last one will be the JM, also one optional parameter. All those optional parameters has default value. You can check details in Meta website. We can also choose to output those results from terminal into the output txt file. So to summary, as we can see here in Meta, we have the queries and the raw data. But our ideal format will be like this. So with each document, we have the query ID, the score for those 4 features and the relevance. However, for now, we don't have a dataset with corresponding relevance judgment. That's why we want to choose the Microsoft Research Latta dataset, since this one has the corresponding scores, the queries, and the relevant judgment. So in the end of the semester, we hope we can find a perfect dataset with the judgment, so we can start from Meta.
Now let's take a look at the Microsoft datasets. The dataset contains 5 folders. Each folder has a training data and a testing data. This is the example of our training data from folder 1. And this is the testing data. Each folder is around 2 gigabytes, so there is lots of data. Now let's take a look at the data format. The first column will be the relevance judgments. The relevance judgments are obtained from a retired labeling set of a commercial web search, the Microsoft Bing. And the relevance has 5 values from 0 to 4. 0 means is irrelevant, and 4 means is perfectly relevant. Since this is the Microsoft research data, we consider the accuracy is relatively good. And then the second column is the query ID, and then the remaining columns will be the feature list. We use 4 of them. The first one is BM25 ranking function for the whole document. The second one is the ABS ranking function for the whole document. The third one is DIR for the whole document. And then the fourth one is JM for the whole document. I would like to mention Meta also has these 4 ranking functions. So the weight vector we obtain from this data set can also be applied later for the Meta. And now we extract the data from the Microsoft datasets and formulate them in a way we want. The first column is the query ID, and then the ranking function scores and relevance. And also the position of the vector will be the document ID.
So now we will apply the SGD on the later dataset. First, we will sampling pairs with different ranking relevance. As you can see here, we want to generate documents with document pairs with same query ID but different relevance rank. So here, the document 1 and document 2 are related to the same query 1, but they are with a different relevance. As here you can see, the document 1 is more relevant than document 2. Since we only want to use the 4 score of it, we will write the pair in this format. A document with its score and its relevance will be used as label later. As to our pairwise approach, we want to find a classifier W to determine the comparative relevance for the 2 documents, which means whether document 1 is more relevant than document 2, or the vice versa, according to same query. Then we will make every pair into a point for the later implementation in the format of doc1 minus doc2 with the difference in relevance. So the array point shows the difference between the 2 documents. The feature space will be the difference in the 4 ranking scores, and the label will be positive 1 or negative 1. Positive 1 means the first document is more relevant. So here's an example point. As you can see here, in the feature vector, every element is the difference in the ranking score, and the label will be the difference in their relevance. In short, we denote the truth label as y, and denote the point vector as x, the weight vector as w. Every element in w is corresponding to the ranking function in x. As you can see here, the w1 is related to BM25, w2 is related to AWS. So the key vector is really important. It is what we want to learn from our algorithm. We will predict. Our prediction rule is as follows: w times x. If it is greater than 0, it means we predict document 1 is more important than document 2. So here's how we do our prediction. If our prediction is consistent with the truth label, there will be no update. The formula is y times w times x greater than 0. There will be no update. Otherwise, we will update the weight vector w. The update rule is as following: new w equals to old w plus r times y times x. This is the perceptron algorithm in SGD, which is derived from the loss function. The r here is the learning rate. We set it to 1, but also we can set it to other values. The y is the truth label, x is a prediction vector. All of the above is what we do in the SGD algorithm. To sum up, here's our pipeline. We will first generate a pair and then make prediction and decide whether we need to update our weight vector w, and do this two steps for several times. Finally, we will learn the weight vector w. The learned weight vector can also be considered as showing the importance of each ranking function. For example, if the w is 10, 1, 1, 1, 3, it means the BM25 is more important than the other 3 ranking functions. Now, we can compute the score combining 4 ranking functions using this w, and for every document, we calculate the new combined score and then rank the documents based on this new score. So now let's briefly go through the code. The code is not very difficult. So first we will read data from the fold, from like this kind of folder, the folder 1 or folder 2, and then do the sampling. Sampling is to get all of the possible pairs which will be used later. Then these are sub-functions, and the learning is the most important part. So for the learning part, we will first get a pair from the sampling pairs, and then for every pair, we will first calculate the truth label y, and then calculate the feature vector, which is the doc1 minus doc2. And then we will make our prediction by w times x. This is our prediction, and we times it with the truth label y. So it is y times w times x. If it is greater than 0, we will do nothing. Else, we will do the update to update the weight vector. So this is how we learning, and the weight update and compare some other functions are right above. For the test, we will nearly do the similar process and save how many pairs we were correct, and then calculate the accuracy. So here is the pipeline of it. We will read data, train it, and learn the weight vector, and print it out. Moreover, we will also test on other ranking functions, like we set the training vector to be 1, 0, 0, 0, 0. So it means we only use BM25 as ranking function to get the related accuracy, and we do the same for ABS, DIR, and GIM. and we will compare their performance later.
Now we obtain our weight function W from training, but how is our ranking function's performance compared to that of other 4 ranking functions individually? Here, to be clear, we are only evaluating the performance of relative order of document pair from different relevance level. For example, if we have an accuracy of 100%, it only means if the 2 documents come from different relevance level, we can classify them, all of them, correctly. In other words, it does not guarantee a perfect ranking performance. This is something important to keep in mind. Now let's take a look at the actual output. Surprisingly, our learning to rank ranking function has an accuracy of 100%. On the other hand, the other 4 ranking functions individually do not perform that well. BM25 only has an accuracy of 56%. ABS has an accuracy of around 56%. DIR has an accuracy around 56%, and JM has an accuracy around 55%. So this shows our learning to rank ranking function that combines 4 ranking functions has a better performance than any individual ranking function. Now take a look at the output from data of folder 2. Surprisingly, again, our ranking function has an accuracy around 100%. And the other 4 ranking functions individually does not perform so well. They have an accuracy around 56% to 57%. So this again shows our learning to rank ranking function improves the performance. Future work. We plan to apply our learning to rank ranking function to all data of 5 folders. We also plan to run our learning to rank ranking function on more data to check if our learning to rank ranking function actually has great performance. Most importantly, we plan to find testing data with a complete ranking. As previously mentioned, the current accuracy performance is only about the relative order of document pair from different relevance level. It does not guarantee our learning to rank ranking function has great performance on overall ranking. Therefore, we need to find testing data with actual ranking to see if our learning to rank function has great performance. Thank you.